In this video, we'll learn how to use the HTG form to go through an entire hypothesis test. We have an example here that says you are conducting a study to see if the proportion of women over 40 who regularly have mammograms is significantly less than 0.84. You use a significance level of 0.10 and obtain a sample of size n equals 508, in which there are 415 successes. So the hypotheses are already given here, but we're going to do this as if that part of it wasn't done for us so we can see the whole process from start to finish. So as I'm reading, I want to start organizing the information that's given, and the what we know section will be any sample statistics that we have or any other relevant information, and then what we believe will be the claim as a statement in words. So let's read. We have, you are conducting a study to see if the proportion, so we know what the proportion, that means I'm going to use the parameter symbol of P for my hypotheses and my claim. The proportion of women over 40 who regularly have mammograms is significantly less. So that's my claim. And I know that it's always an equal sign for the null hypothesis, and that if there's no equality in the claim, it will become my alternative. And less than what? Less than 0.84. We also have a sample of size n, 508, with a number of successes x that is 415. And that means that our sample proportion, p hat, would be x divided by n. We also were given to do this test with a significance level of 0.10. So I'm going to go ahead and put that down here. And I'll put my claim in words, even though I already kind of did the other steps. The proportion of women over 40 who regularly have mammograms is less, significantly less than 0.84. All right, so we've taken that claim statement and put it into symbols here. And I think we've used all the information that they've given us. I'm going to go ahead and put that down for now. And this is a left-tailed test because of the symbol in my alternative hypothesis. And which sampling distribution should I use? Well, you can look at the hypothesis testing reference sheet and see that the only test statistic formula with P in it is the one that has a Z-score. So you could remember it that way, or you could just remember that for proportions we always use the standard normal distribution. And now we're ready to start the curve sketch. And the curve sketch is really the most important part of all of this. But you can't get the curve sketch right if you don't do those first few steps correctly. So the curve sketch is going to be completed when we have marked it with the significance area and its corresponding critical value boundary, and the test statistic boundary, which is where we take our sample proportion and turn it into a Z-score. And that boundary will have an area attached to it called the probability value. So let's go ahead and begin our sketch, just a rough draft, because we won't have it exactly right until we find some more values. But it's good to get a visual. So we said this is a left-tailed test. So my critical value will be negative. And since we're doing a z-test, it'll be a z-score. And we find z-scores by doing norm.inverse, so it's the reverse lookup with the normal distribution, and we give it a left area, And the mean, which if it's a z-score, the mean is always 0 and the standard deviation is always 1. And the area that we have to the left of this boundary is the significance. The significance here is 0.1. So I can use that to find my z-score. So I'm going to do that here. Norm dot inverse with a probability of alpha to the left, a mean of 0, and a standard deviation of 1. And notice that I've also put in here that it's a z-score and it'll be negative. Okay, so we have negative 2.82. What did I just say? Excuse me, while I fix that. Negative 1.282. All right, so now we've completed the red couple. Now we have the green couple to do, and we'll start by finding the test statistic. We're going to calculate that by converting our sample proportion into a z-score. So the z-score is going to be negative also because the sample proportion we were given, 0.817, is less than 0.84. So if on the graph we have 0.84 in the center, that would be my sample proportion. I meant to say my population proportion if the null hypothesis is true. And that would have a corresponding z-score of 0. And whatever this sample proportion that we got from the sample is, which here it is 0.817, that's going to be somewhere here on the left too. And that will be a boundary. And let's just say it's here for now, 0.817. That will create an area to the left called the p-value. So it's the probability of getting a value at least that extreme. So if this probability is smaller than the red region, then we'll reject the null hypothesis because it'll mean that this statistical result may not have happened by chance, and it could be that the null hypothesis is false. So by converting this value into a z-score, we can see where it falls in relationship to this critical value. All right, so we'll do the z-score formula for proportions from our formula sheet, and that is z test statistic z equals sample statistic minus claimed or hypothesized proportion value and divided by the standard error PQ over N. Now, P is the claimed value and Q is 1 minus that. So we'll do it here. If P is claimed to be 0.84, then Q would be Q would be equal to 1 minus P. Okay, so when we go to calculate our sample statistic into a z-score, we will have 0.817 minus 0.84, and then divided by the square root of P, 0.84, times Q, 0.16, and all divided underneath the square root by the sample size of 508. So we have in the numerator P hat minus P, close parentheses, then divide by the square root of P times Q divided by N. So now I have my test statistic value of negative 1.418. So my sketch now will make more sense if I make it a little neater. Let me pause and fix it up for you so we don't waste video time. Okay, so now you can see my population proportion of 0.84, if the null hypothesis is true, would have a z-score of 0 right in the center. My critical value is at negative 1.28 as a z-score, and my p-hat, which is 0.17 as a proportion, has a z-score of negative 1.418. So my p-hat is farther away from the population proportion than the critical value is, and that means this is a significant result. So I could say by comparing boundaries that the test statistic is more extreme, in other words, more rare, and less likely to happen by chance than the critical value. Therefore, we will choose to reject the null hypothesis, H sub 0. Right? Now we can also compare areas. So let's put the areas on our sketch. We have from the critical value, we can draw a line up to make our significance region, also called the critical region, and also called the probability of a type 1 error. Here that was 0.10. And it's also called my rejection region. Notice that my test statistic falls into that red region. So we could say the test statistic falls into the rejection region, therefore we reject the null hypothesis. Now we can also draw a line up from the sample statistic z-score, the test statistic, and do an area to that side from that boundary, and that would be our p-value. So let's find out what that area is. The p-value is found using norm.distribution, and we want to give it the boundary, which is our test statistic, the mean of 0 and the standard deviation of 1, as always for z-scores, and 1 for cumulative. So now we have our area of, when it rounds, we usually round to 3 significant digits, or 4 decimal places is a good standard also. So 3 significant digits here would be like that. So we have a p-value of 0.07 compared with an area of 0.10. So notice that when the test statistic falls into the rejection region, the p-value will be smaller than the significance level. So we have a smaller chance of this test statistic happening by chance, which means that this claim might be false, and we have reason enough to reject it. So we can say that here. The p-value is smaller than alpha, or you could say than the significance level. Therefore, reject H sub 0. Now, the most important thing is that we are choosing to reject the null hypothesis both times, and that should always be the case, because if one is true, the other has to be true. If my test statistic is farther into the tail than my critical value is, then automatically that means the area to the left of it will be smaller than the area to the left of the critical value. So now we're ready to draw a conclusion about the claim. Remember that this step always talks about the original claim and never about the null hypothesis. So I'm going to word my conclusion using the context of the problem. So I'm going to say Here's my claim in words. The proportion of women who regularly have mammograms is significantly less than 0.84. Okay, so let's see. How would I word this? I would say the sample data support the claim that the proportion of women over 40 who regularly have mammograms is significantly less than 0.84. And the reason I can say that the sample data support the claim is not just because I rejected the null hypothesis. That's one of the wordings you can have when you reject a null hypothesis. The reason we use that wording in this case is because our claim was actually contained in the alternative hypothesis. So when we rejected this null hypothesis, we were able to support the alternative. And again, the alternative contains my claim, but that's not always the case. So I advise you to maybe put a little note about where the claim falls. You can put like a little C. Sometimes it'll fall under your null if there's equality in the statement of the claim. And in that case, you would end up rejecting the null hypothesis. I meant to say, if you reject the null hypothesis, then you would also be rejecting your claim. So watch the wording. If you get confused, there is a flow chart in the reference packet about how to do your final wording. So that's the hypothesis test. Now sometimes you may also want to do a corresponding confidence interval. So we have another part of this page that we can do the confidence interval that would be suitable to match up with this hypothesis test. So the claim in this case was that P is less than 0.84. So if I construct a confidence interval for this proportion to estimate the true population proportion, I will use the sample information to make that estimate. I'll take my point estimate and expand it with a margin of error into an interval estimate. And if my interval estimate is fully below 0.84, then I will have support for this claim. Another way of looking at it is if it's not fully below 0.84, then it may contain the null hypothesis, and then the null hypothesis might be true. So if it's fully below 0.84 and it does not contain the 0.84, then I could kind of say I'm rejecting the null hypothesis in that sense. But what we do is we look for evidence that the alternative is true. So the alpha for our confidence interval will sometimes be the same as the alpha you had in your hypothesis test, and sometimes it won't be. Sometimes it'll be twice that amount. And if it's a one-tailed test like we just had here, then you'll have two tails for your confidence interval. So this makes sense because you want to match up the left-tailed area. Let's see our sketch again. You want to match up this left-tailed red area of 0.1 with the left tail on your confidence interval. And since confidence intervals have two tails, then you'll have to double that up. And the reason they have two tails is because, let's see if I can explain this without taking up too much time. With the confidence interval, we have this claimed proportion, and we're looking at that claim, or no, I meant to say our sample proportion of 0.817. So with 0.817, if this is our center starting point, our point estimate, and we're going to expand that in each direction by a distance of E, the margin of error, then in between those boundaries, I'm going to have my confidence level. The confidence level is the area in between. And then out in the tails is half of the complement of that on each side. So since I need to match up this side with my hypothesis test critical region, and I have to have a twin over here, that would mean that I have a total tail area of 0.2. And so that would mean that my confidence level will be 1 minus that 0.8. Right? So there's an area of 0.8 in between and an area of 0.10 in each tail. Well, all that means is that your critical value will be the same as it was in the hypothesis test. So that's also an easy way of remembering. So my alpha here is 0.2, which is 2 times the significance level. And that's only because I had a single-tailed test. If this had been a two-tailed test to start with, I wouldn't need to do any doubling. It would already be a double tail. So the area in each tail is 0.1. And that's why the alpha is twice that much. And the confidence level is 1 minus the alpha. And the critical value is the same as the critical value from our hypothesis test. But make sure, oopsie, too far. But make sure that you make that positive. And to make anything positive, you can just wrap an absolute value around it. Okay, so next we have another place to put our critical value. We'll just get it from up here. And we're going to use that critical value and multiply it with our standard error to get a margin of error E. And this is coming from the formulas in the sheet. On the left side under confidence interval is p hat plus or minus the margin of error, which is calculated with the critical z value, times the square root of p hat q hat over n. So the standard error, p hat q hat over n, or I meant to say the square root of p hat q hat divided by n. So p hat is this times q hat. Well, q hat is 1 minus p hat. So 1 minus p hat and divided by n, 508. It's yelling at me because I didn't close my parentheses here. When you nest something inside of another function, you have to make sure to close your parentheses. Okay, so now I can calculate my margin of error just by multiplying my critical value, z-score, times my standard error, and then take my point estimate, which is your sample statistic p hat in this case, and add and subtract that margin of error we just calculated. Let's put some more on there. And let's go ahead and do the excuse me, round off rule for proportions is 3 significant digits. So I'm going to go ahead and round this to 3 places, and also we'll go ahead and do that for this one as well. So our lower boundary will be the point estimate minus the margin of error, p hat minus e. And the upper boundary will be p hat plus e. And the parameter symbol in the middle is p. That's what we're estimating, the population proportion, p, not p hat. So with 80% confidence, we believe that the true population proportion is between 0.8 And we need to give some more decimal places here. Let's go to 3. So we believe with 80% confidence that it is somewhere between 0.795 and 0.839. So notice that my claimed value of 0.84 is not in that region. And in fact, both boundaries are less than 0.84. So because of that, I would interpret this confidence interval in regards to the claim by saying the confidence interval does not contain the claimed P of 0.84. Furthermore, the interval lies entirely below 0.84, indicating that the null hypothesis, or I meant to say the alternative hypothesis may be supported. Okay? So it's kind of like getting an amen on the decision or the claim that we already made using the hypothesis test. So we're getting confirmation here from our confidence interval. So that's from start to finish. And you want to try to do as many examples as possible because things change quite a lot from problem to problem. So I'll do another video where the scenarios are a little different, and some of the things that you have to consider will change. Let's just talk about that real quick. What are the things that can change from problem to problem? You could have the type left, right, 2. You could also have the distribution, the sampling distribution. Could be Z or T. And the population parameter that you're doing a claim about, the parameter, could be mu, or, and it could be mu with sigma known, mu with the sample standard deviation S known, or a proportion. And the sampling distribution can be merged with this because if it's a claim about a mean with sigma known, it'll be a Z distribution. If it's a claim about a mean with sigma unknown, it'll be a T distribution. And if it's a proportion, it'll be a Z. Can't get rid of that. Try this again. There we go. What else can change? We can have, say, left, right, 2, different parameters with different distributions. We could also have, we could end up rejecting the null hypothesis, and we could end up rejecting or not rejecting, fail to reject null. And let me just go there. The claim could be in the null, or the claim could be in the alternative hypothesis. So that creates 4 different possible endings. So when you merge the different places your claim could fall, or you merge that with the decisions you could make about the null hypothesis, you can do kind of a tree diagram to see this. The claim in the null, you will either then from there reject or not reject. And if the claim falls in the alternative, then we will still have the possibility of rejecting the null or failing to reject the null. So 4 different things. If your claim is in the null and you reject the null, then you are rejecting the claim. If your claim is in the null and you fail to reject the claim, then you fail to reject the claim. Notice we don't say accept the claim. That's improper. If your claim is in the alternative and you reject the null, then you have support for the claim. And if your claim is in the alternative and you fail to reject the null, then you fail to support the claim. Okay, so 4 different endings. And these are summarized in your reference packet.